Chapter 9, Laplace Transforms. Learning Outcome 9.1 and 9.2. Describe how and why Fourier transforms and Laplace transforms are related. Describe what a region of convergence means. The Laplace transform of a signal is given by the following integral. It's very similar to the integral we used for Fourier transforms. We integrate from negative infinity to infinity our time signal with an exponential e to the minus st dt. S is a complex number, but not a purely imaginary number. We say that the output of our transform is x of s, again capital X, and our variable is s instead of j omega. This is also called the two-sided or bilateral Laplace transform. And we use the notation with an arrow because x of t is not equal to x of s. X of t will have variables of t, x of s will have variables of s, and they should not have the opposite variable in them. And sometimes we use the script letter L around our time signal to indicate that we're taking a Laplace transform, and L inverse to indicate that we're taking an inverse Laplace transform. This is notation you will often see and need to be familiar with. So let's consider this integral. If we look at s, I said it was a complex number. It's going to have a real part and an imaginary part. We substitute that in for our s. We can then break up that exponential into having the real exponent and the complex exponent. Note that if sigma is equal to 0, then we only have the complex exponent, and that's going to be identically the Fourier transform. We're going to use this in a later learning outcome when we talk about how to get an approximation of the magnitude of the Fourier transform from the Laplace transform in a pole zero plot. Let's consider an example of calculating the Laplace transform of a function. This is an exponential decreasing starting at time 0. We take our definition of the Laplace transform, the analysis equation for the Laplace transform. We substitute in for x of t, the function we were given. Note that because of the u of t, that's going to change our limits of integration. That's how we deal with the u of t when we have it inside of our integral. It just changes our limits, and that u of t then is a 1 between the set of limits, and it goes away. When we integrate, we now need to evaluate that at our first limit and our second limit. Now let's consider that case. Let's look at the second term first, because the second term is easier. We have an e to the 0. E to the 0 is 1. And we can then take all these negatives and cancel them out and turn them into positives, which is a lot easier to look at. Now let's look at this first term. This first term has an exponential, and that exponential is partially real and partially imaginary. We can break it into the real parts and the imaginary parts. This second term here has a magnitude of 1 and will never go to 0 and never go to infinity. This part here is real, and this here will have an exponent of infinity. Depends on whether the quantity minus a minus sigma is positive or negative. So if minus a minus sigma is less than 0, then we're going to have e to the negative infinity, which goes to 0, which means this term goes to 0, and our integral converges, therefore region of convergence. Saying that minus a plus sigma is less than 0 is the same thing as saying positive a plus sigma is greater than 0, or that sigma is greater than negative a. Because sigma is the real part of our complex variable s, we can replace sigma with real of s, and this is how you'll see it written. That says that this integral will converge whenever the real part of s is greater than 0. That's our region of convergence for this initial time function, this signal. So real of s greater than negative a is our region of convergence, ROC. Now that we know what our ROC is algebraically, what does it look like graphically? Here's the complex plane. S is a complex number in the plane. We want to consider the region. It's greater than, so it's not a line, it's a shaded area. The region in the space where the real part of S is greater than negative a. Please pause the video and sketch the curve. The real part of S is equal to negative a is along this line, but we don't have equals, we only have greater than, so this is our border, but does not include that line. And when we're greater than that, it gives us this region here. That is our region of convergence for the signal we were discussing. You have a table 9.2 in your book of Laplace transforms of many common functions. This is very similar to table 4.2 and 5.2 in earlier chapters, where we have a signal, a time signal, and we have its transform. But this table has a new column, which the other ones did not have, which is our region of convergence column. Look for the signal in this example, which is transform pair 6, e to the minus a t u of t, gives us a 1 over s plus a, which is what we calculated, and states the region of convergence which we derived. All of them will have a region of convergence. You need to know where they are. Note that there are multiple signals in the second column which have the same transform, which give different time signals because they have different regions of convergence. You cannot invert your transform without knowing your region of convergence, because you wouldn't know whether to choose 6 or 7 if you knew that the transform was 1 over s plus a. This column is very important and will inform all of our work in Chapter 9.